Thank you very much. So today I would like to tell you a little bit about process-based industrial AI, and in a moment you'll see what I exactly mean about process-based AI. Usually when people talk about manufacturing, they talk about predictive maintenance. Predictive maintenance is usually about constraining the insights to a specific region of the manufacturing production line. For example, usually it's about the aging process of different machines and are about estimating time to failure, like in survival analysis coming from statistics, and being able to predict the next failure of different machines. When you do that, you actually ignore any other part of the production line. So suppose you are focusing on a specific machine or on a specific asset, then you are ignoring the rest of the production line. And this is a major deficient because usually in manufacturing production lines, error propagates from upstream to downstream in the production line. And so if you do not account for this propagation of error or propagation of failure, say, then your results are very limited and very constrained to the specific machine that you're interested in. So we are not going to talk here about predictive maintenance. We're not going to talk about tolerance of machines and aging of machines. And we're not going to talk about aging of humans also. So we will focus the talk to things that are process-driven, meaning that some of the failures are process-driven, meaning that they start at some point in the production line, probably somewhere upstream, and then they accumulated along the line of the production line, which can be as simple as a linear production line or more complex than that. I'll show you in a moment. But there is some propagation of error, say, in time and in space. It's much more complex, much more challenging, but much more rewarding because you're using more of the data and not a limited amount of the production line assets. Let me say a few words about Seebo. Seebo is an industry 4.0. It's also referred to usually as smart manufacturing or the fourth industrial revolution. It's an industry 4.0 startup with the main mission to predict and prevent losses in production yield and quality. Again, problems that occur because of some processing issues. Again, about error that propagates or accumulates during the production line lifetime. We address problems of a quality, waste, and throughput that are process-driven in several verticals, such as the chemical industry, the food and beverage industry, and also the automotive industries. We've built a general or a generic and scalable solution that acts upon all of these verticals. These verticals can vary from a continuous processing manufacturing process to batch-specific or a unit-specific, more of a discrete processing manufacturing. So usually in the chemical industry, we're talking about continuous manufacturing. So think of a certain liquid or substance that gets produced. And in the food and beverage industry and in the automotive industries, we are mostly talking about batches or units. Think in terms of an engine block or a tire. So we have the whole range from a continuous manufacturing processes to discrete manufacturing process. And we have tried to build a single and scalable and generic solution for all of the range that I've mentioned. So in order to fix ideas, let me tell you a little bit about the problem setup and the pains as we get to see from our clients. And again, these clients come from the chemical industries and the automotive, which apparently without prior knowledge, it seems like a totally different ball game. But still, you can have a generic solution for these three verticals. If you talk to process engineers in the plants, you'll see that the aim of any manufacturing plant is to act or produce products in as much stable state as they can. So usually in the beginning of a lifetime of a plant, a few smart engineers come up with a design, and they come up with values and ranges of different parameters of the plant. And starting from that point, people in the plant, the stakeholders in the plant, usually they do not want to deviate from these ranges or from the initial design. So gaining trust, part of our insights is to say to these people in the plant that the initial design or the initial values and ranges of the parameters that they are working with are not stable enough. And if they will perturb a little bit these ranges, they will get much more stable process and will get more products. So the general aim is to be stable as possible. Deviation from being non-stable can take many different forms. So the goals are usually to reduce waste or produce more products in better qualities. And the need from a process-based AI solution is usually twofold. Again, when you talk to process engineers in the plants and other stakeholders, like foremen, they want to know two things. They want to know what are the chances that they are going to hit an incident, however you define it, in next, say, 30 minutes. And also being able to understand, so prediction is usually just the beginning of the road, not the end of the road. Beyond the prediction, they want to know why on average things go wrong, and also why a specific incident had happened. So they want to make sure, they want to understand things globally and also incidents locally. Not only that, they want to take all of the insights that we provide them about specific incidents and to be able to correlate or to find common causes of groups of incidents. So our starting point in every plant is the production flow blueprint or the plant topology. We have what we call a digital twin, where we model the plant topology or the network of the plant. So usually these are production lines. There's an hierarchy usually in this plant. There are production lines. There are different assets within the production lines. There are machines within assets, and there are sub-machines within these machines. And then at the end, you have many sensors, or in this industry, they're also called tags. So there are many tags and sensors scattered along the production line. We have the plant topology. We have between 100 and 1,000 of sensors installed. We do not install the sensors. We make use of the data that's coming from these sensors, but we do not install the sensors. I will talk a little bit probably in the next slide maybe about the subtleties and complexities that come along with this type of data from these sensors. Each one of the sensors may come from a different they can be of many different kinds. Some of them are already old enough. Some of them are not valid anymore. And even in that case, the plant people usually do not know about that because this whole era of Industry 4.0, or these plants are in their infancy in terms of absorbing or adapting machine learning or AI solutions. So it's like high-tech meets low-tech. This is a mantra that I like to say, that when we come to these plants, we see magnificent people, but we have to remember that their nature is not, they are still in infancy in adopting these kind of solutions. So again, gaining trust is a major issue. And even if we have an algorithm that we feel that behaves with 99 precision and recall, it's still a major issue to come to these people and tell them you have to switch gears now and use our recommendations. It's not as easy as it's very. I mean, it's very difficult, especially because they really like to stick to the initial design of parameters that the engineers have set up maybe 30 or even 70 years ago. So, thousands of sensors. We also have data that's coming from raw materials or recipes, depending on the verticals. And the thing is that we have to define a specific problem. I'll say about that in a moment. Examples could be, think of the chemical industry where a certain substance or a fertilizer is being produced, and the level of concentration is a thing that they are interested in. This is one example of a problem that can be easily defined. Another example that's coming from both the food and beverage industries and also from the automotive industry is about monitoring or predicting or even explaining proportion of defects. So, besides modeling the plant topology or the production line blueprint, we are working on this under a supervised paradigm. And so the first thing that we do is we translate the business problem. It can be the waste, the amount of waste, or the throughput, or the quality of the product being produced. So we take the business problem and translate it into a mathematical formula or formulas. So it's fascinating because when you come again to these people in the plant and you ask them, what is it that you are trying to reduce, or what is it that you are trying to predict? It's very hard for them to define it in terms of stochastic processes and time series meaning. So we work together to translate the business problem into a main problem, but still the main problem can be very difficult to absorb, because sometimes you care about an abrupt change. Sometimes you care about not having 7 spikes in the next hour. And what exactly spike means. This is also something that we need to talk about. Sometimes people are interested in gradual change, and sometimes we give them a set of 5, 6 different kinds of deviation from stability. And they say, what do you think they say? They say, all of them, I don't care. But then when we translate it to dollar value, we see that it does make a difference whether you are predicting or explaining a specific kind of target or the other. Anyway, we translate the business problem into a main problem and then use the plant topology to define what we call proxies of the problem or sub-problems. So we have an hierarchy, we have a main problem, which by itself can have multiple definitions, and we have an hierarchy from that main problem into sub-problems and proxies of the problem, because sometimes they know that in the exactly middle of the production line, they have some measurements about some quality, but it's a bit shaky, and only at the end of the production line they get the real measurement of the quality. So in that sense, we have a proxy or a surrogate of the main thing that we're trying to explain and predict. Usually, this is what we call target vectors. The translated business problem into a mathematical or a machine learning problem is measured in line with a certain resolution. But sometimes we get more data of the same thing on a sample of data where they produce offline measurement in some laboratory tests. So it's a major challenge to incorporate these inline and offline measurements, because if you want to predict something and the offline takes 10 hours, then the patient is already dead. So still, even though we cannot, in some cases, we cannot use the offline data, the offline measurement, quality measurement, we cannot use it in order to produce predictions. We still can use them to have better explanations of why sometimes things go wrong. And again, the problem that we are dealing with have to be process-driven or process-related, and nothing that has to do with, again, with the tolerance or aging of a specific machine. I'd like to tell you a little bit about data challenges associated with process-based industrial AI, especially because of the fact that some of these plants are very old. They can be, as I said, 70 years old or 100 years old. And still, the sensors have been installed probably in the last 20 years, not in the last 70 years, but still, it's a totally different, it's a legacy industries, and totally different than the lifetime of a startup, of a high-tech startup. In terms of stochastic processes, we are dealing with thousands of time series data or stochastic processes, which we cannot assume any stationarity or any mixing-like conditions about them. They want to act in a stable manner, but still it's a very dynamic environment. And every change that they do may change any value of any of these time series data. So we get to see major, what is known as covariate shift. We get to see many different distributions from 1 month to the another, or from 1 week to another. The distributions of the target vectors or the target tags sensors that we've defined are changing, and the distributions of these thousands of sensors change. There are many correlations between the input sensors and what we call the target sensors, and the data is extremely irregular, coming with different resolutions. Some of the sensors are called set points, meaning that they set the value that they want this tag or sensor to have. And then there is its corresponding, it's called a PV sensor, that's measuring exactly, it's the twin of the set points. And so you sometimes want to look at deviations between the set points and their corresponding or twin PVs. Data is extremely irregular. Most of the sensors are changing from week to week. Even the frequency of the problem itself, like in the frequency of the machine learning label or target, can change abruptly from one, it can be like 3% waste in 1 month and 75% in the next month. And this is mainly because they've started a different campaign. They were able to identify some possible causes of the process. They did some changes. Sometimes they don't even tell us the changes they do. And then the frequency of the problem changes from 3% to 75%. In both cases, it's imbalance. But in the first place, it's like it's in the other direction. One other issue is that because there are 2 dimensions here, the time and the space. So it's a production line. You start at this point and you end up at that point where quality measures are being produced. And in order to come up with a supervised solution, you have to match between upstream data and downstream data. So I usually like to describe it in this way. We have time series data. We have multiple time series data, multiple target and sub-problems data, and you want to be able to shift or shift each one of these input sensors relative to the target sensors in such a way that you get maximum correlation, whatever correlation means. And so the problem is that you usually don't have this information. We usually do not know by how much we need to, what's the time lag, but by how much to shift each one of the input sensors relative to the target sensor. On top of that, not all of the production lines are simple as a linear production line. Linear production lines, they started at this point, that end up in this point, and it's roughly easy to deal with. We usually get to see these kind of production lines in the modern automotive industries, producing, for example, engine blocks. But in the chemical industry, we don't have these kinds of easy production lines. You have parallel production lines, where in this case the matching or the shifting becomes much more complicated. And even much worse than that, in the chemical industry, sometimes the produced material, the substance or whatever it is not good enough, but still they can bring it back, there's a loop back. They can bring it back into a midpoint in the production line and reproduce it. And so this is not even a DAG, a directed cyclic graph. This creates a major challenge in terms of what we call traceability, the ability to match each one of the ability to shift correctly. There's also many other data that we have, like production events such as stoppages and maintenance and new sensor installation, and whether the new campaign had started, yes or no. It's in short, it's a very dynamic environment, and if you do not adapt frequently, you're going to get not just bad results, but totally no results, or providing no insight at all, or maybe providing the opposite insight. Some of the clients are working as a multi-product settings where they can produce in the same day different products. So there's what's called a changeover. There's a changeover period between one product to another. Sometimes we have multi-batch. Sometimes we have mini batches. We have different ingredients that are associated with different batches. And so in a total, it's a very dynamic framework. Some of the problems end-to-end, what's called the takt time, is 40 minutes, and in some other processes is like 8 hours or even days. So building a generic data science pipeline for all of this dynamic data is extremely challenging. So I will, as you see, I will focus in this talk mainly on the data itself and how to pre-process it in a smart way. So, as I said, we have time series data. So apart from doing the standard time series pre-processing stuff like aggregation and resampling and pivoting and making the data regular in some sense, we also follow the multiple imputation paradigm where you try different, it's like an ensemble methods of imputation, where we try different kinds of imputation methods and aggregate the results in some reasonable way. For that purpose, it's very important to understand that each one of the tags, each one of the sensors come with different resolutions. So it makes a lot of difference if you impute missing values in a 2-hour period, if it's a sensor with 1 second resolution or 3-hour resolutions. So we also learn the resolution dynamically of each one of the sensors. We also adapt to the different distributions that are changing of each one of these sensors. A major issue is invalid or faulty time periods. Sometimes, even more than just sometimes, some of the sensors become invalid in some sense. The stakeholders in the plant, they don't have monitoring system for that. They do not know that, and we cannot count on that. So we have to, for each one of the sensors, we want to be able to estimate the start and end time of the period of time where we think that the sensor is behaving in an invalid way. So I'm not going to get much into this, but we define a weight vector or a weight number for each one of the examples in the data that accounting for the shakiness or the noisiness of the data. So usually, you can find correlation. Usually, the same set of sensors coming from the same physical space or the same machine in the same experience the same invalid periods of time. So you can use the fact that we know exactly, or almost exactly, where each one of the sensors is in which machine it is. As I mentioned, traceability is a major issue. Again, it's the ability to take all of the input sensors that are measured upstream in the production line and the output sensors, or a translated business problem into different calculated sensors that we call the target vector or the target vectors. So be able to have an optimal match between these two without almost any prior knowledge. The idea is to find the optimum lag or the optimum shift between these two sets of time series data, and we're talking about like thousands of sensors in the input sensors, and say tens of sensors, of target sensors on the other side. So let's say x1 up to xn are our sensor values, and suppose for simplicity that we have a very schematic and simple linear production line, as depicted here, in which we have k machines. Again, it's almost never as simple as in here. But suppose these sensors are grouped into k machines, and there are k machines. They produce something, and at the end they measure the quality in some sense of each one of the units, or maybe of a gallon of a liquid. The shift, and suppose for simplicity again that we know exactly the duration, the processing duration of each one of these machines. Let's call them D1 to DK. So this shifting is very easy. We only have to take this vector of durations of the machines, reverse it, and take the cumulative sum in order to shift each one of the sensors within a machine. So for example, suppose it takes 20 minutes to produce the material in machine K and 30 minutes to produce in the machine K minus 1. And so you have to shift the sensors relative to the target. It's always relative to the target. So you have to shift all of the sensors within the kth machine by 20 minutes, and then shift all of the time series or the sensors within the K minus 1 machine by 50 minutes, 20 plus 30. Sounds easy. But, as I mentioned, it's not easy. We do not know. The production line is usually not linear. It's maybe parallel. It maybe has loopbacks, and it's much more complicated than we think. Durations are almost always unknown. Sometimes when we talk to the process engineers in the plant, they say, yeah, I think the kth machine is between 20 to 120 minutes. So it's a huge range, and usually we have only a minimum value for the duration and a maximum value. not more than that. And we sometimes do not even count on that. And even if we did know the exact duration, processing duration of each one of the machines, because it's a very dynamic situation, then these durations change from time to time. Actually, they change continuously. And so you have to come up with an algorithm or an optimization objective, with an objective, in order to find it in a dynamic and online fashion. So what we're trying to set up is the following. We are trying to find the, so once we know the duration, time's up. So yeah, I'll wrap it up. So once we know the duration, we know the shift. And we sometimes have only knowledge about the distribution of the duration. So suppose we know only that it's between 20 minutes and 120 minutes. So we can assume a uniform distribution of weights and then sample different duration from that distribution, compute the shifts, and compute some performance metric of some machine learning model. It can be a simple correlation, or it can be a full machine learning model. So we're trying to maximize a metric F of some machine learning model subject to changes of the durations or changes in the shifts. This can be cast as an instance of a Bayesian optimization. In Bayesian optimization, probably most of you know about it. Bayesian optimization, usually we have an expensive function to compute, and we have some prior knowledge about the distributions of the parameters. So again, here we have an expensive function to compute, some performance metrics of some machine learning model, and we may know that the distribution of shifts or the distribution of durations is uniform. If we have more than that, sometimes we can have more data and we can estimate the exact or more accurate distribution. It can be a normal distribution, for example. But when we don't have this data, we start with a uniform distribution, and we follow the Bayesian optimization paradigm, where you start with a certain prior on your F. You start with a certain prior on your F, and then you optimize a surrogate model or a probabilistic model representing F. That's the probability or the likelihood of F given the shift. At Seebo, we use the 3-parson estimators because 3-parson estimators, what it does, it differentiates between lower values of the densities and upper values of the densities. But in our case, and the densities are usually estimated using kernel density estimators, which are known to suffer from highly dimensional data like the one that we have. But in our case, we can use a type of a Toddler's first law of geography because we have the plane topology, and it's reasonable to assume that like a naive Bayes approach, where the distribution of sensors, of shifting of sensors within the same physical space are more correlated than sensors far apart. So sensors within a certain machine at the beginning of the road and at the end of the road probably or obviously have different shifts, therefore different distributions. So we can use the machinery of the Bayesian optimization to sample different durations, meaning we can compute or sample different shifts of the time input legs relative to the target legs, and then compute the metric. And we do it in a continuous manner because, as I said, it's a very dynamic environment, and you cannot just do it like once in the lifetime of deploying a machine learning model or data science model in one of these plants. So to recap, I think what I was trying to convey here today is that it is a jungle out there in terms of data, and it's extremely challenging, and therefore trying to solve it is a joy. Thank you.